So, students, we are going to continue on our discussion on the quasi-chemical approach of genesis of different phase diagrams. As I told you that in this approach we are basically using thermodynamical techniques to analyze the genesis of different phase diagrams. As you know, the formation of different phases depends on the free energy, and in material science we use more frequently the Gibbs free energy as a measure of stability of different phases, which is given by G equal to H minus Ts, where G is the Gibbs free energy, H is the enthalpy, T is the temperature and S is the entropy. So, by using quasi-chemical approach we basically calculate the expression for H and S for solids and liquid solutions, and then see how the different parameters of that expression affect the phase diagrams. So, I discussed with you how we calculate H. H is the enthalpy term, and enthalpy can be calculated using bond energies of different pairs, and for that I assume there are two elements A and B, and therefore, there are two types of atoms in the solution or liquid solution A and B, and different bonds which can form are AA type, BB type or AB type. So, therefore, depending on the bond energies, the enthalpy is given by a term like XAA, number of bonds of AA, HAA is the bonds energy of AA type bonds, YBB, HBB, where YBB is the number of bonds of BB type and HBB is the bond energy of BB, plus WAB multiplied by HAB, where WAB is the number of bonds of AB type and H is the bond energies of AB. So, and using the formalism which I have discussed in the last class, you can get this expression as like this. You can write down this is equal to Zn by 2 into XA HAA plus X1 minus XA HBB plus twice XA 1 minus XA HAB minus HA plus HBB by 2 like this, correct. So, this is what we can get. Z is the coordination number, N is the number of atoms present in the system, X is the mole fraction of A, and HA is the bond strength of AB, HAA is the bond strength of AA type bonds, and HBB is the bond strength of BB type bonds. And I hope you last class I have discussed this expression and you have already got idea how to derive it, because I left some steps behind so that you can work out and get the expression correctly. So, now this is the expression of enthalpy as a function of mole fractions, Z is the coordinate number and the bond energies, as you can clearly see. And in this case, as I told you, Z is a positive, N is positive, XA is positive. So, therefore, the value of H depends on sign of H rather depends on the sign of these term, difference of the bond energy of AB minus average of bond energies of A and BB type atoms. So, therefore, this is the prime factor controlling the sign of H in this term. Now, let us look at whether can I get HAA. HA is the enthalpy of pure A, enthalpy of pure A, and it corresponding to x equal to 1, because pure A x equal to 1, x b equal to 0, and therefore, I get this is equal to Zn by 2 HAA. You can clearly see this is equal to Zn by 2 multiplied by HAA. So, similarly HB enthalpy of pure B can be obtained when x a equal to 0, right, then x b equal to 1 because we know that in a solution or liquid solution x a plus x b equal to 1. So, for pure B x a will be 0, for pure A x b equal to 0 or x equal to 1, whatever it is, and this equal to Zn by 2 multiplied by HBB, correct. So therefore, if we have a physical mixture of two elements A and B, in which the mole fraction of A is XA, mole fraction of B is 1 minus XA, then because XB is equal to 1 minus XA, right, that is why. So in a solution or liquid solution, if in a physical mixture, not a solution, physical mixture, if you have XA fraction of A and XB fraction of B, then the enthalpy of the system, enthalpy of mechanical mixture, I write mechanical mixture, enthalpy of mechanical mixture of AB will be equal to what? Would be equal to XA multiplied by HAA, right, XA multiplied by HAA and XB multiplied by HBB, that is correct, and XB multiplied by HBB. So that is equal to XA multiplied by HAA plus 1 minus XA multiplied by HBB. So as you clearly see, that is actually, so and that will be multiplied, sorry, this will be multiplied by Zn by 2, this is the number of bonds, Zn by 2, correct, because this is the total number of bonds present in the system. So now as I clearly see, this term is exactly equal to the first two terms of this expression, expression number 1. For you can see in the expression number 2, this term or expression number 2 is equivalent to the first two terms of the expression 1. You can clearly see that. So therefore, any change of the enthalpy because of solid or liquid solution formation is given by the third term very clearly, because this is the enthalpy of the mechanical mixture of AB. So therefore, any change of enthalpy because of solid solution or liquid solution must be equal to this term, third term. So I can write down delta Hm, which is the enthalpy change because of solid solution or liquid solution formation, is equal to H minus HAB mechanical mixture, and that is equal to Zn XA into 1 minus XA. You can clearly see these two and these two will get cancelled, multiplied by HAB minus HAA plus HBB by 2. Okay. So this is the enthalpy change because of the solid solution formation. This is the term given by. As you can clearly see in this term, this is a function of XA square. So that means this term is, it will be the nature of this term, if temperature is constant, Z and N are constant, and at a fixed temperature AB, bond energies of AB and BB and AA are constant. So therefore that will be a parabolic nature, because it is XA square, H is proportional to XA square. Fine. So that is why I told in the many times in the class that why the free energy expressions G is basically parabolic, inverse parabolic in nature. Okay. Now as you know, this is for H, that is fine, we have calculated. So we need to also calculate the S, entropy, and I would like to tell you here that we have already done these calculations in the some of the classes, but I will do it again. So I will keep this term, I will write it at the top, and rest of the thing I will erase. So I keep these three things here, one is G, other one is delta Hm. So delta Hm is Zn XA multiplied by 1 minus XA HAB minus HAA plus HBB by 2. I erase everything else because I need to derive the expression of S, entropy. But at this point I would like to tell you that we are more interested more in the delta terms, not in the absolute value of H and S, the change because of the formation of solution. As you know, entropy in a statistical mechanics way is determined by the number of ways you can arrange the atoms in a lattice for a solution. That I have already told you, right. So, as Boltzmann had told, the entropy is given by this expression K, L and W, where K is a Boltzmann's constant, that is nothing but R by N. R is the universal gas constant, N is the Avogadro number, and log of W is this, where W is what? W is the probability of distribution of the atoms on the lattice side, that is the thing. So, this tells you the probability of distribution. So, now to cut the thing short, because I have already discussed, so I will not go into detail of that, but to cut the thing short, suppose in a solution you have n number of lattice points, n number of lattice points, let us suppose, and you have small n number of A atoms and capital N minus small n number of B atoms to be arranged on the n lattice points. This is what is the task. So, suppose you have a n lattice points and you need to arrange small n number of A atoms and capital N minus small n number of B atoms in that n lattice points, and this arrangement, the most probable arrangement, will give us the entropy or entropy change rather. As you know, if you have pure A atoms, suppose you have only A atoms and you want to arrange A atoms on the lattice sides. So, there is only one way of arranging lattice sides. Suppose you have small n number of A atoms, you want to arrange on the small n number of lattice sides. So, there is only one way of arranging them, you cannot do much. Similarly, if you have capital N, suppose small n number of B atoms, you want to arrange them on small n number of lattice points, then arrangement will be same, there is no change. So, I can write down delta S or change of entropy because of this arrangement can be written as SAB minus SA minus SB. What is that? Well, that is because of this term. This is the entropy of AB solution. Suppose I have got n A atoms plus n minus n B atoms and I am forming a solution n A n minus n B atoms solution. So, to do that, what is happening? If I have pure A, then this is the entropy. If I have pure B, then this is the entropy, and if I have solution, this is the entropy. So, entropy change is given by this minus this, and this can be written as ln, okay, let me take common K ln WAB minus ln WA minus ln WB, right, that is what it is. So, as you know, as I told you, arranging pure A atoms on lattice side, it does not change any distribution, it will have a probability of 1. So, therefore, this basically equal to ln WAB, am I right? That is what it is, because these two terms, this is log of 1, this is log of 1, so log of 1 is 0, it will get cancelled, and this can be written as k ln factorial n minus 1 factorial n, let me see it whether I have done it here, yes, k ln factorial n capital factorial like this. What is this? This is the permutation combination, factorial n, capital N of factorial, factorial capital N, factorial mon L, and n minus 1 factorial, or n factorial divided by small n factorial multiplied by n minus n factorial. And you know that you can apply Stirling approximation. What is Stirling approximation? Log of n capital is equal to L log n, it is approximation minus n. This is called Stirling approximation, Stirling formula actually, he has given long back. So, you can apply this, finally what you will get? You will get k, I am not going to write down everything, finally what you will get? K L log n minus n log n, remember this n is capital, this n is small, minus n minus small n log of n minus log n. Just because I am just doing lot of step jump, that is why I am using my notes. So, finally, this can be written as minus n k, okay, x a log of x a plus x b log of x b, okay, where x a is given by small n by capital N, x b is given by n minus n by capital N. This is what is, because this is the mole fraction. Okay. If you have total number of A atoms n, total number of site is capital N, then this is the mole fraction of A. Similarly, mole fraction of B is total number of B atoms divided by total number of sites. So, that is the my entropy change. You can clearly see n is positive, k is positive, this is a Boltzmann constant, n is the capital Avogadro number, and these terms are negative. Log of x a is negative because x a and x b are what? They are all fractions. So, therefore, they are negative. This can also be written like this in terms of single variable x a. Okay. So, this is my delta S term. I would like you to derive this yourself, otherwise you will not be able to feel the mathematics. You will be, you will be simply going by the motion. You should do yourself and get this expression on your notebook. When you are listening this lecture, switch off the lecture and then you try to derive this expression on yourself. So, I have got delta S and I have got delta H. So, now I will erase and I will write down what is delta G, because that is what is the most important factor, correct. So, delta G is the change of free energy, and change of free energy is given by delta H minus T delta S. So, what is that then? That is given by, okay, let us do that. So, delta H is delta G is delta H minus, so let us write down M also, and M should be here, T delta S M. So, that is given by Z n x a multiplied by 1 minus x a H a b minus H a a plus H b b by 2 plus n k t, this minus will become plus x a ln x a plus 1 minus x a ln 1 minus x a. That is what it is. So, this is my delta G m expression. So, these three expressions is what is we are going to use for all our future descriptions of the solid solution or liquid solution. So, now let us analyze it. Okay. First thing you should do pointwise, let me just do pointwise. So, I erase this part, this is better, I erase this one also, but it is there. So, we will analyze pointwise one by one. First point is that this is a whole thing is a function of x a square at constant, is a function of x squared at constant temperature and pressure. Clear? Delta G is a function of x square. Why? See, at Z is a constant, N is a constant, and at a constant temperature these bond energies will be also not changing, they will be constant. So, therefore, this is, I told you already, this is 1 minus x square, or is a function of x square. This one is also like that. If you expand log, it will be 1 minus x a, first term if you consider. So, x a into 1 minus x a is x square, again 1 minus x a, 1 minus x a, x square, and nkt is also constant at a constant temperature. So, therefore, the delta G, if you plot at a constant temperature delta G, if you plot this delta G curve as a constant temperature, it will look like a delta G versus delta Gm versus x b if I plot, or x a, okay, x a if you plot. So, x a will be 0 here, 1 here. So, this will be a parabola at any temperature T equal to T1. That is clear. So, all those free energy curves I have drawn in the different phase diagrams are now clarified, that why this shape is present, why you draw this shape. And this is a very important lesson you must not forget all your life, because most of the courses across different departments in India, the instructor draw this diagram, but never explain why this diagram is like this, why it will have looks like a parabola, why it looks like inverse parabola, never explain. This is basically because of this mathematical expression, and which I have derived from bond energy calculations. So, that is why both the terms are parabolic in nature. So, total thing will be parabolic in nature. That is the first thing, first point I would like to make. Second thing is that, as you see here this term, so delta G, as you have already learned, delta G is the change of free energy. So, for any process to happen spontaneously, delta G should be negative. That is what is been told you in thermodynamics. Remember, I am not teaching thermodynamics, I am taking phase diagram course. So, these basics you must have it. So, for any process to happen spontaneously, delta G must be negative. So, delta G has two parts, this is first part, this is second part. This is the entropy change, which is always negative. Why? Because n is a positive, k is a positive, t is a positive, this is a negative, always x a is a fraction, and so therefore 1 minus x is a fraction, a log of any fraction is negative. If you have 0.5 log, it will be negative, 0.2 log negative, 0.9 log negative. So, any fraction if you take a log, it will be negative. So, that is the thing actually, therefore entropy terms, entropy change will be always negative, and that actually that is why we form solid solutions or liquid solutions very easily. This is the main reason, because entropy trivializes the formation of solid or liquid solutions. On the other hand, delta G actually depends also on enthalpy term, and the enthalpy term, positiveness or negativeness of the enthalpy term, as I told you, depends on relative magnitude of these bond energies, very clearly, relative magnitude of these bond energies, this completely depends on that. So, now, so that means what? There are three situations possible. For delta G to be negative, delta S is always negative, there is no problem. So, therefore, for delta G is to be negative, delta H must be negative. When delta H will be negative? Okay. Before that, let me clarify. Bond energies are always negative, we know that. If something forms between two pieces, A or B or AB, bond energies are negative. So, this is only possible when, HAB, the bond energies or enthalpy of AB, that is equivalent to the bond energies of AB, is less than or equal to half of HAA plus HBB. If this is less than, both all are negative. If this is less negative, then this term will be negative, because there is a negative sign there. In that case, delta G EM will be negative. So, therefore, a solid solution will form when this condition will be satisfied. In fact, this condition means what? This condition means the bond energies of formation energies of bonds for dissimilar pair between AB is lower than between AA and BB. Okay, that is the thing you should understand. So, bond energies between AB is lower than the average bond energies of A and BB. That means what? Dissimilar atoms will be forming more easily bonds than the similar atoms, and this leads to superlattice formation or ordering or formation of order compounds like Ni3L, Fe3, FeAl, all those compounds I talked about in the phase diagram. This condition is met. When this condition is met, we will have this compound formation. So, you can explain the formation of this compound by simply form Quasichemical approaches. Now, this is the second case. Third case is what? Third case was delta G sign will also depend on both these two. So, as you see here, delta Sm is always negative. So, therefore, whether if delta H m is positive, there are two situations possible, two subcategories are possible. One, two subcategories possible. One, when the relative magnitude of this one is much lower than relative magnitude of, means relative value of this one, not sign, relative value of this one is much lower than this one, then delta G m will be negative. So, when relative value of delta H m is much lower than delta S m, then delta G will be negative, obviously, because the value of delta S m will be so much so it will supersede the value of delta H, whether it is positive does not matter, but situation will be changed when delta H m value is almost similar or greater than equal to delta S m, then we will have different situations. And so, with this I stop here. In the next class briefly I will explain the 3B condition, what will happen. So, you have understood clearly that there are three situations, three different conclusions we have done. One is the shape, other one is the first thing where both of them are negative, is very easy, superlattive forms. Then third one is what will happen to relative magnitude, and the last one which I will discuss is when delta H m is 0. So, these two things 3 and 4 I will discuss in the last next class and clarify it to you. Please practice this whenever you are taking this lecture.